All right, we're alive. February 9th, another day. Let's do this. Let's do today's challenge. All right, there's nothing for us to check on the highlight on the notifications. Go right into it. Ooh, it's a tree. All right, let's see. I like trees. What's it called? Convert BST, the binary search tree, right? Yeah, binary search tree to greater tree. Oh, what the hell is greater tree? Given the root, convert it to a greater tree such that every key of the original binary search tree is changed to the original key plus sum of all keys greater than the original key in binary search tree. And it rhymes. Alright, this is just describing what binary search tree is. We know that already. This question is the same as the other one. To greater tree. Hold on, let me read that again. Every key, I mean that's the value. I think when it says key, it actually says it's value. I think it's value of the original tree is changed to the original key, the original value plus sum of all keys greater than the original key in binary search tree original key. So this plus everything here, which is that's with 11, 18, 26, 30. Okay, let's do this. Oh, everything. So not only these, but also everything. But it's just 30 plus 2, 3, and 1. That's 36. Yes. Okay. We kind of already find some patterns in here. For example, this one is everything added together, and this one is everything add this and this together. So this one will be this plus the value in here. Because we're talking about everything bigger than this. Everything bigger than this is everything else. Everything bigger than this is everything else plus this. Everything bigger than this will be everything here. The root. Oh wait, it will be this. Well, this is smaller, but minus this was 35. Hold on. I'm trying to find the recursion here. All right, so actually, see, so this is where we start. All right, the rightmost node is the biggest. Is that correct? Yes, the rightmost node is the biggest in the binary search tree. So 8 is by itself, and then we go to the parent of 8. And then we know the left child is the smaller, so we don't really count. So we don't count the right child. So this one will be 15, right? And then going up, its parent. So its parent, we also look at the right tree, and then we can just use this value 15 plus itself is 21. And then we go to the left child. Now that is the difficult part because we go to the left child, anything bigger will be everything, right? Everything. So bigger than this will be its parent, but not the grandparents. So until we basically add its parent to it, give us 26. That's correct. But then when we consider this, we have to consider the entirety of this tree, because that's the one that's bigger than the root, right? Anything bigger than the root is the entire right tree. So we somehow need to return. So once, say we go to here, now we do some operation here, right? So we need to update its value, and at the same time we need to return the total value of this thing. I think these are the total value. Yeah, total value of this thing, and return here. So this we can get is 4 plus the total value. That's that. And then, so we are kind of going right tree first. We're going right tree, and then we go to the root, and then with the left tree. I'm gonna get some water. All right, water is here. Let's keep thinking. Now, if you are on the left child, on the left side, so your parent is bigger than you, so you need to add your parent for sure, and also you need to add your right child, your right thing. So we're gonna go here. So basically, here we're gonna go here, here, right? And this one will be 3. But it cannot be 3 because we need to pass this value down. So every time we go to the left, now every time we go to the next child, we have to pass the value. And how do we reason this? We go to the left child, and we need to, every time we go to the left child, we need to pass yes, because we go to the left child's value is the parent's value, always has to add the parent's value and its subsequent. And then we go right child, then we don't have to pass, but we still have to pass the most root value. So we'd have to pass 30 to here, and this is the right child, and then it go down to this. All right, let's think about it again. So we start from here, and we go right child, right? We go right child. So for a root node, it needs its parent. In this case, the parent is 0. And then it needs everything on the right side, the total on the right side. And a total on the right side. And that's it. The parent and total on the right side. That will be here. And then we go to the right child. Right? I want to go to the right child because it's bigger than. Now we always go to the right child first. And because we go to the right child, we don't have to consider the root because the right child is bigger than the root. So we go to the right child first. And for this, because it's the right child, so it doesn't. So we just pass a 0. So because the parent contribute a 0 to the right child, so we just pass a 0 here, and then this one a 0 and all of its right child. So this is the same. This is the same. And then this, and when we go to the left child, we have to pass in the contribution from the parent. The parent can be obtained already by the right child. And then we pass in, and then this will be good. And after the left child is done, we just need to return the root of not the root, return the value, this value. So this value, we just return it back up. I think I might have sketched it up. Let's take a look. see if this is correct. Yeah, recursion is always fun to sketch up, and could be a little bit, mind twisting from time to time, but it's good exercise. No, good exercise. All right, let's see. Convert. We probably don't want to do this. We probably want to define a new function. I just call it DFS. It says a DFS no matter what. So we have a node, which is the tree node, and we need to also passing a value is, we call it parent contribution. That's too long. How do we pcont? How about pcont? Parent contribution. That's going to be an int. And I'm going to return an int. Right? It's the total, the sum of all the values in including the node and its children. All right, so here we go. What do we do? If not node, then we return 0. Don't change anything. All right. If else, we're gonna go to the right first. So we're gonna go DFS node.right. We go right first, and because I'm going right, the parent contribution is 0. And we're gonna say right contribution is this. Now we have the right contribution. We need to add, so we have our node dot value equals the parent contribution plus the right contribution. That's the node dot value. And after I update the node dot value, I go left, and I actually return the left contribution. So we're going to go node dot left, and I pass in my parent contribution to the left. And that will be it. We're just going to call. We're going to call DFS root parent contribution is 0, and then we going to return the root. So we change it in place. Now we cannot run tests. Now we can again, but I'm too lazy to do that. So let's just run the test cases here. All right, let's take a look. It is not correct. Oh, because I did do. It did not record the values. That is weird. I thought I can record the values. Why the value is not recorded? Node.val equals oh, plus node dot plus add. I forgot the node dot val itself. Not correct. Not correct. What did I get in return? Let's just take a look. Oh, I got the exact, not exact the same thing, but okay. So it did not work. We're trying to figure out why. So 8, I still got 7 here. I did get this, but this is not updated. All right, let's see. Let's see. not no. So right contribution will go no dot right 0, and then come here no dot right 0, no dot right 0, and then we go no dot right 0, and then we return 0. We're back in here, so no dot value equals parent contribution is 0, that's, and right contribution is also 0, so this one's 8. That's good. And then we're gonna return dot left, and then dot left is a 0, so this one returns 0 to here. That is the issue. We do not return 0 when you visit the left child. If the left child is empty, we are going to return the parent contribution, because the left child is going to be, so left child is the same. It's the parent contribution plus itself, and so if there's no left child, then we need to return parent contribution. Expected a binary search tree with unique values. Oh, I give it a wrong. That's not the test case. Huh? What am I doing? That was the same as before. Yeah. That looks promising. That looks very promising. We have one error, I think. We have a 3 and a 5. Huh. All right. We're getting closer. I think we're getting closer. Let's take a look. So 8. So on the right side, 8, 15, 21, 26, 30, 36. Here are the issues. Oh, because as I go to the right, it shall not be 0. It is p cont. It's parent contribution. Yes, this shall be right, because as we go to the right child, there is contribution. You have to keep passing the contribution from your parent. Oh my goodness, this looks terrible. Oh, this is not right. Hold on. Do we really do this? No. I think I'm a little bit. Let's try an easier case. This case seems to be a little bit too difficult. Let's try this case. This case looks easier. See if we get this one right. Now this has to be 0. This has to be 0. But we will probably do a different thing later on. Let's just see. All right, so the easy case pass. How about this one? Yeah, this one shall pass. I think this one will pass. Yeah, this one pass, and this one, maybe this one is our thing. Okay, let's see if this one pass. This one also passed. So the problem is I need to add, let's see, 3 to 4, 1. If we add another value, 5, this one might not pass. Invalid test case. How is this invalid? Oh my god, of course it's invalid. It's not a binary search tree. Dude, it has to be, oh man, very restricting. So let's do this as a 1, and this becomes 0, and this becomes 2. Yep, It's not correct because the 2 does not get. So this is the result I get, right? This is the result I get, which means I got correct here, correct here, correct here, correct here, but this one is not right. So when I go to the right child, it is not. I passed the wrong thing. Okay, so I want to analyze this again. So I'm going to use the regular test case, run it, and collect this, put him back here. All right, just kind of analyze. So when we go right, it's correct, right? And then we go left, it's correct. We got this one right. And then that's the root, right? We have the root, and then we go to the left. We have already done the root. And then we go here. And we go here, go left, we have the parent contribution 30. So we're passing 30 here, right? 30 is here. And then we got to this, and then it's going to go right. So when this go right, I'm passing 0. But in fact, I have to pass in the parent contribution, which is 30, which is this one. I have to pass this down. But if we go this parent contribution, and then we see that all the other things kind of mess up. I mean, why would the other things mess up? If we pass parent contribution on this line down, it's still going to be 0, right? And then we go here, go up. This one doesn't affect. This one has parent contribution here. And then go up, and then passing left, shall still be 30. And then we're just passing 30 down. Wait, why would this not work if we go parent contribution? What do we get? I think I got like some gigantic number. Come on, man. I kept doing this. Yeah, in this case, if we still cannot resolve it, we'll have to go get our big guns and then start debugging on this side. All right, we have some ridiculous numbers here. Trying to make sense. What happened? All right. On the right-hand side, 8, 15 is correct. 21 is correct. How come this becomes 47? How come you become 47? All right, so let's stand on this. So node val equals p count, which is 0 at this time because we go 0, 0, 0 down. It's still 0 plus a right contribution. Right contribution is 15, which give us 21. And then we go to the left. We go 21 to the left. How come you become 47? I know, because I say if not node, return parent contribution. So when I go to the right, which passed the parent contribution, and then it returns back to me, so I'm adding double the 21. Yeah, it's 21 plus 21 plus 5. All right, which means I just do not. So if I go right, if there's no right child, I shall return 0. And if there's no left child, I think I just need to change this a little bit. Like if there's a right child, I do this. And if there's no right child, I don't do anything. So we're kind of avoiding this. So I think we can do if node.right, else 0. It's no right contribution if there's no right child. and then return this if node.left has a left child, we're going to return. If there's no left child, we just return a 0, right? If there's no left child. So from my perspective, if there's no left child, I do not return 0, I return myself. And let's check it out one more time. Run. It's still not 100%. Let's see what went wrong this time. All right, we got correct on the right side, and we have trouble here. We got 33, which means 30 is passed down. So again, we come here. We have right contribution, right? We have right contribution. We have the right. We go here, which pass down the p count. Now p count, when we do the left, because I go left, it's 30. So 30 passing down here. And then we go right, 30 goes here. And we go right again, 30 goes here. And then right contribution is 0, so nothing. So its p count was 30 plus right count is 0, and then plus itself, 33. Perfect. Then I return. And it's no left child. And I return itself. I return 33. Oh, I return 33. And then when I return 33, this becomes 33 plus 30 plus 2. So we add it twice. Man, oh man. Let's think about this node. What is this node looking at? It's just its right contribution and its parent contribution, right? The right contribution shall not consist of the parent contribution, because otherwise the parent contribution will be counted twice. So this shall just be the right contribution, that's itself, which means when we return, what do we return? We shall return the value that is not the right contribution. No, not including the parent contribution. So if we go to the right, and then we done it, and then when we return, we get the right contribution. And what type of contribution are we talking about? We're talking about the contribution by itself, without the parent contribution, because we already add the parent contribution here. So this shall be the one without parent contribution, which means when we return, it shall return the one without parent contribution. And we already added it, right? We already added. So it's going to be node val minus parent contribution. That is the true, the one we return is the true sum of all the nodes on all the nodes including myself, right? All the nodes. So it's basically, we can also call it, but we already added it, so this is okay. Let's try it one more time. I have faith in this one. Probably don't have to do this. I think that's already in the clipboard. Let's try it one more time. Oh man, it's still not right. Now I think I have even deeper issues. Again, these are all correct. So the right is all correct. And now when we return this if no dot left. So what did we return? We only returned 5. Oh my god. Hold on. What we return is everything. That's the sum, right? The sum of the sum of everything. Okay, hold on. What we want to return here is 26, which means it is everything that's everything combined. Everything combined. That's the one we want to return. Everything that is combined. We want to return that. For example, for here, for this one, I want to return 5. And for here, I want to return all these added together. Right? Yeah, that's what we want to return. That is what we want to return. Now, how do we find this? Well, we find this is going to be left contribution, node.left, node.val, if node.left, else it's going to be 0. Because if we don't have, then there's nothing. Then when we return, we are going to return so we have a parent contribution. Parent contribution. So node.val is everything. So it's going to be node.val plus left contribution. Isn't that what we're looking for? Because when we return, we have node.val is myself plus the right contribution. And with the parent contribution. No, we don't want to return the parent contribution. We don't want to return the parent contribution. So we need to remove the parent contribution and add the left contribution. So in this case, I have 21. And the parent contribution is 0, so I remove 0 and I plus 5 to 26. And then say here I have parent contribution is 30. Right contribution shall be 3, because when I'm here I have parent contribution 30 plus right contribution is 0, so I'm 33. Left contribution is also 0. So what I'm returning is my node value is 33 minus parent contribution 30 plus 0. That's 3. All right, let's try this one. Let's try this one. Okay, let's try this one. All right, this one looks promising. This one looks very promising. I'm actually going to submit it. I think this one's correct. Runtime error. What the hell? Oh. Because I removed it. Should we check? Oh, in that case, we can do if not node return 0, and then we do this, and then do this. That is correct, and I think this can handle. This can handle the edge case. Yes, we got it. Wow, comparing to our previous version, it looks very different now. All right, let me copy and paste this. Yeah, like I said, trees are interesting, but it does take a lot of mind power, at least for me, to reason with it. It doesn't change too much. It doesn't change too much. So I think the difference is we need to realize what do we want to return. Like previous version was a little bit convoluted because the return value is not very specific. Like when we return from a root node, right, from a node, it shall return the sum of everything, right, the sum of everything. And we do that by this, right, by this. So basically, I think we can probably do it even with a simpler way. I mean, I need a left, I need a right, and I need a parent. Those are the three things: the left, the right, and the parent. And then the only thing that matters is the right, and then the parent. Yeah, that's what we do, right? We have the parent contribution coming in, and then we do. Yeah, I think this is about right. This is about right. If we take a look at the runtime, it's that was shocking. Never had this good before. We had 99% ranking. All right, let's have the summary here. It took quite a few iterations to come up with the correct recursion. The main obstacle was that the return value from a node was unclear. It should be that we always return the original sum of all the values in the subtree, including the subtree node subtree. So the workflow is like this. Each node's altered value equals its parent contribution plus its right child's contribution. That is p count plus r count, and plus itself. Because its parent contribution plus its right contribution plus itself. So plus node.val. And the return value of a node is its updated node.val, its updated value, which consists its updated value minus parent contribution plus left child's contribution. That is node.val minus p count plus left count. this is essentially the sum of L count plus right count plus node plus original node dot val. It's ON because every node we visit once, and we run it at 68 milliseconds, which has a 99% ranking. Yeah, I don't get this good ranking very often, so very happy about the outcome. And let's take a look at how the people solve it. Maybe they have better solutions. It's a medium, I think. I think it's a medium question. Yeah, it's a medium question. Recursion. Ooh, look at this. Iteration is that's the same as recursion. Yeah, I don't like this, but it's good. The reverse Morris in order traversal. It take a lot of effort to write it, to make it right, which I think it's not really necessary. All right, let's take a look. Recursion. The root is not none. Oh. We convert. All right, so this is actually so without writing a DFS, right? Without writing a DFS. The root is not none. Okay. We convert right. All right, so we think more in big picture. Right? This is kind of drilling down, but now we want to think more in bigger picture. So we convert a right, and after we convert a right, we do the total. All right, so when we convert a right, root dot right convert. Hold on. Self dot total plus equals root dot value, and root dot value equals self dot total. Okay, and then we go to the left. Oh, self dot total keeps changing. Oh, self dot total is the total number, the total values of everything. So we go right, and every time when we hit a node, we increment the total, which means the total just keep adding, keep adding, keep adding, and then after we add the total, we update. We update the node's value. All right, let's take a look. Coming back in here, give us some visual cues. So basically, we have a total to keep adding everything. Right, so we go all the way down here. We add an 8. So we record, going back up. Then we go left, but left is nothing. And we go up 7. So basically, we will say, what I'm going to do is for this, I'm gonna just change my left, change my right first, and then change my right, update myself, and change the left. And the way I update myself is myself plus everything on the right side. So we have something to keep track on the sum of everything on my right side. And then I update myself, and then we go to the left. And then I have the total number of everything here. Now we go down here, and this will be everything here, and then go back up, and then it will be a little bit more because we added 3. And then we're done. Wow, okay. It's the same concept, but I actually like the solution better. Reverse in order traversal. No. No, I do not want to reverse in order traversal. Linear time, constant space, yeah. Recursive retrieval step methods. and use the null pointers of the tree's leaves to create a temporary link out of the left subtree. Allow the traverser to perform constant additional memory. Yeah, it's just back. So basically we go here, so we don't have to I think the point is you don't have to use a stack, and then you can go back from you can go back. Yeah, so you go right, and then nothing. Then you want to go back to the parent, and then you already set up this, so you can go back this way, and then you go here, and then this, and you make a link here, go here, so we can go here to the parent, and then go hit the parent. And this, okay, this, go back here. How do we set left pointers are listed in blue, right pointers red. Dashed indicates temporary links. During the algorithm, which will be erased before it terminates. Blue edges can be dashed. Oh. Successor. Oh yeah, I remember. So like from this, I need to find what is the shoot? I think the thing is to find the first. So we go to the right and to find the leftmost. To find the leftmost child. Yeah, I think that's to find the leftmost child. It's not none, and the left is not node. We go to the left, to the left, to the left, until we find the leftmost. Yeah, the leftmost child on a right branch. And then we here, we find the leftmost and we create a link. Okay, if there is no right subtree, then we can visit this node and continue traverse. Oh my god, I need to make this a little bit bigger. I can't even read it. There we go, that looks better. Continue traversing if right is none, and total value is total. So keep traversing left, and if there is a right subtree, there's a node that has a greater value than the current one, therefore we must traverse our node first. So we have a right, so we can get the successor, okay, and then if the successor got left, if so we get a successor, right? We get a successor. If the successor, wait, isn't the successor to the left is always none? There's no left subtree in this branch of control flow in temporary connection. If success to the left is none. Oh, if the success to the left is none, we make a connection. When there's a temporary link, success to the left equals node. And no, we move to the right branch. And then what? And then we go back up. And then we do the regular traversal. If the right is not none, then we go here, we keep making this temporary thing. We keep making the temporary thing, and then until we hit one is the rightmost. And then we add a total. then node equals node dot left, right? Equals node dot left. So this will, oh, hold on. So I hit a node. If node right is none, when we're talking about the then node equals node dot left. Is a node dot left this time is not none. All right, so we are so when we haven't reached the end yet, right? So we already trying here. So this is a while, not, but if it is, here, like it is a situation, we only have one right child. And then we say if this is not none, we go left. If it is, then we just return this node. So this node goes back, right? That's the left. Goes back. So we go node dot left. We actually go back to the parent node. Go back to the parent node, and then we go back to the parent node. But if we go back to the parent node, node dot left, node dot right is not none. Oh, here we go. I didn't read this part. Yeah, so we already go back. So this time we already did the magic, and then we find the successor again, and then this time successor on the left is not none because we already used the magic. So we clear the magic, and then that means we are at the up value. So we're gonna do this. We visit the right first, right? We visit the right first. So we just add the total, we get it, and then we do its dot left. Now, if the left has, and then we basically just, oh, I don't think, honestly, I don't think I can write this like out of like blind. It takes a lot of practice to write it. Constant space. How are we come up with this? Yeah, we can. We can come up with this. This is not really. This one, yeah, it's not easy. Yeah, this is not easy. But it's definitely doable, right? It's definitely doable. And we kind of pray that the interviewer would never ask for a Morrison traversal. I mean, if they can. I mean, I think the ideal is if they ever ask you, can this be done in O1 space, and we should say yes, it can, because there is something called a Morris traversal. Oh, is that called reverse Morris traversal? I mean, it's in order, so it's reversed, but it's a Morris traversal which uses temporary links to go back to the root without using a stack. But honestly, if they want you to implement it, you can just say, "Can I Google it?" I don't think it's really necessary. All right, but I do want to implement the smart one, so we're gonna do the smart one now, and hopefully the smart one will come very easy. Yeah, I actually still remember. I'm gonna say this is the official recursion solution, which uses a counter to keep track of the current of the sum of the nodes visited. since we are visiting the right branch first, the sum is always the largest nodes encountered so far. So when I don't know the ranking, I don't worry about it. We are going to define def initiate self. When we do a self.counter total. Yeah, completely using their notation. It's fine. And we don't need to do this. Right? We don't need to do this. All we need to do is, we have it, if root, right? If root, then we gonna convert self.convert. We're gonna convert root.write first, and then after we convert the right, we have the total, which is everything on the right. So we say self.total plus equal to root.val, and then root.val equals self.total, and then we self.convert root.left, and we're done. Wow, this is logically, it is also easier to explain. Run an example, see if it works. Surely it did. Submitting it. Yeah, it doesn't matter. The time complexity does not really matter that much, but I'd rather use this one, and if I need like a input for production. Very straightforward, very simple to reason with. All right, I'm not gonna do Morris. Just always keep in mind there's something called Morris traversal that can do a DFS in O1 space. I think that's the end of it. All right. I don't really think it's necessary to go through this. It's pretty self-explanatory. All right, that'll be it. That'll be it for today. I'll see you guys tomorrow. Adios.